All right, well, here's target 4D, and this will help you analyze your weather maps a lot better on your city weather map project. 4D says explain isobars and how differences in air pressure and the Coriolis effect create wind movement patterns. So, I'm going to take you through this. First, we're going to talk about isobars and what an isobar is. All it is a line of equal pressure on a weather map, and we see these all the time. You'll be seeing them a lot on your weather maps. Each line is letting you know the gradient or the change in pressure by millibars. So bar means pressure, iso means equal, so isobar, equal pressure. So areas on that line have equal pressure. You can kind of think of it as a topographic map or a contour map where you can think of it almost as an elevation is how some people think of it. So we know that winds flow counterclockwise around lows. We studied this last unit. And winds flow clockwise around highs. And winds blow or flow roughly parallel to the isobars. So when they're blowing from high to low, you can see here on these arrows, right? They're flowing out clockwise, and they gradually transition over into these different lanes. They don't blow directly from high to low, but they swirl out kind of like this due to the Coriolis effect. So wind is caused by air flowing from high pressure to low pressure. Its direction is influenced by the Earth's rotation. So in the northern hemisphere, our high pressures spin outward clockwise, and our low pressures spin inward counterclockwise, and essentially air feeds from one into the other. And it goes from high pressure, you can see here, 1012 millibars all the way to 984 millibars on the low. So why do we really care about this? Well, it allows us to understand how wind moves, or how the air moves, and where the air moves, that's where humidity and temperatures will also move as well. So these lines being closer together, here we have a high pressure, which is outward moving air. Where the lines are closer together, that's a tighter pressure gradient, or you can think of it as water moving through a hose with your thumb over it is going to move a lot faster and at a higher velocity, as opposed to where you have a larger opening for fluid to pass. So that's what this diagram's showing you, fast or high speed wind as opposed to low. So another thing you can learn from isobar pattern on the surface of weather is that spacing. So if you think about it as the same distance, so here at the bottom we have the same distance as up here on this top picture, and we have a very different change in pressure. So if you spread it out over a longer distance, that's going to be a slower wind, or here we have a southwest wind of 10 knots. But if we were to have this many millibars change from 1,000 millibars down to 988 millibars, that's a much stronger pressure gradient. And as you can see here, they're showing it same direction, but 30 knots. So when on a weather map, we can see this. It allows us to see how high pressure and low pressures are moving across our continent. It also helps to predict where weather patterns are coming from and what they're going to bring. So here we have these strong winds. We've highlighted it here in red. We know that they're stronger there in that part of the globe because those isobars are so much tighter together, whereas down here around Texas and Mexico, there's a lot of distance in between differences in pressure for those isobars, so that's going to be much calmer. So that leads us to better understanding the jet stream, where we have highs and lows, or ridges and troughs, and actually seeing how these isobars are flowing helps us to get a good idea of how winds are moving, particularly higher up in the atmosphere. So here you can kind of see that certain line that's highlighted in red is giving you a good idea of where there's big differences in temperature and where air masses are traveling above the jet stream and below the jet stream. So all the jet stream is a current of fast moving air, and this is much higher up in the atmosphere, but it's what really helps to move air masses across the surface of the Earth. Since the jet stream is a result of temperature differences, it's a useful temperature forecasting tool. So you can see how isobars and isotherms are related here. The jet stream shows the boundary between colder air to the north and generally warmer air to the south, and that's why those air masses usually agree with that pattern and then also flow along that movement of air. So as you can see here, we have isobars and it's around a low, and we have fronts which always connect to a low. You're never going to see fronts connected to a high because everything is outward moving from a high, whereas everything is inward onto a low. So that brings air masses together. Where air masses come together, you have fronts. Fronts are that borderline between air masses, and those isobars a lot of times will line up with the movement of the front and kind of give you a good idea of which way they are moving, besides just the direction that the triangles or half circles are moving. So that's kind of bringing it all together. Allows you to see how the importance of pressure and understanding isobars allows you to better predict weather. So that's the end of our discussion about isobars, the jet stream, and isotherms. Hopefully all those things can come together to help you better analyze a surface weather map. Have a good one.